6 says two-dimensional. Here's a review of a one-dimensional, a linear straight line question. A 30-gram bullet moving at 250 meters per second strikes a 5-kilogram wood block at rest and sticks into it. If the bullet and the block move together after the collision on the frictionless surface, A, write a momentum question. B, find the speed of the block after the impact. Ooh, C, find the heat energy created during the collision. Boy, I should have left an entire page for this. I'll do that next time. Okay. Well, A, write a momentum question. Is there a collision? Then my momentum equation is going to start out by saying the sum of all the initial momentum equals the sum of all the final momentum. Before the collision, what was moving? The bullet, the block. How about the wood? So I'm not using B for bullet and B for block. The bullet, the wood, or both before the collision. So that's going to be the momentum of the bullet initial. After the collision, what's moving? The bullet, the wood, or both? Both. Stuck together or separate? Stuck together. Separate, I just list them separately, final and final. Stuck together, it's going to be the momentum of both final. Momentum is what times what? Mass times velocity. So this is going to be the mass of the bullet, its initial velocity, and it's going to be the mass of the bullet plus the mass of the wood, V final. There's my actual equation. So A says write a momentum equation. You could argue that that first sum of is the momentum equation, but if you want to break it down to its component parts, there it is, that third one. A lot of you coughing. Hopefully I don't get it. Nico, what's B ask us to find? Okay, I think what it's really asking me to find is V final there that I didn't put a vector sign on, V final. And because we're in a nice straight line, for the last time today, probably, we'll be able to just divide and do basic math. I'll divide by the masses. V final is going to be the mass of the bullet, initial velocity of the bullet, divided by the mass of the bullet plus the mass of the wood. If I plug in numbers, I'm going to get mass of the bullet 0.03, its initial speed 250, divided by 5.03. Are you okay? I added 5 and 0.03 in my head on the bottom there. How fast will this move off to? How fast will this move off?
1.49.
Sorry?
1.49.
Even?
1.491.
Okay, we'll keep that on my calculator because part C, anytime there's a part C, I assume I'm going to be using something from part B, and I've clued in on that, right? 0.03 times 250 times, Mr. Dewick, divided by, try that again, divided by, there we go, 5.03. 1.4, you know what, I'm going to go, I'll go 1.49. I'll probably use 1.491 later on. So 1.49 meters per second. Sam, what's part C asking me to find? Ooh, this looks like a job for energy conservation of energy, I think might be my first approach. So I think for part C, I'm going to start out by saying the amount of kinetic, the amount of potential has to equal the final amount of kinetic, the final amount of potential, plus whatever's missing must have gone into heat. Do you see any changes in height in this question at all? Then, Cole, my friend, I think I can do that, yeah? In fact, I think if I get the heat by itself, it's really going to be it's really going to be that. And I got to be careful here because I got several different things moving. What's the initial kinetic energy? Hey, what's moving initially? The bullet. So it's going to be a half mass of the bullet, V of the bullet squared, right? 1/2 mass of the bullet, V bullet squared, minus. After the collision, what's moving? Oh, so it's going to be a half mass of the bullet plus mass of the wood, and that's going to be the final velocity squared. If those numbers are equal, then no heat was generated. I'll get 0 as an answer. Otherwise, I may have lost some kinetic energy. Energy was still conserved. Kinetic energy isn't always conserved. Sometimes some of the energy goes into heat. In fact, we had those chrome spheres that were able to char paper. 0.5, 0.03, 250 squared, minus 0.5, 5.03, the mass of both of them, 1.491 squared. That's how much heat was generated. Let's see. 1/2 times m times v squared minus 1/2 times 5.03 times that previous answer that I still had on my calculator squared, and I get about 932 joules of heat. This is actually leading us to next lesson. We're going to look at something called the ballistic pendulum. What's the ballistic pendulum? I don't know if you ever asked yourself, before they invented radar, how did they figure out how fast bullets could travel? It's not like you can stopwatch time it. Human reaction time can't react that fast. So 80 years ago, 60 years ago, if the FBI or the RCMP or someone was doing ballistics and they wanted to try and figure out how fast a bullet was traveling, what would they do? Well, they would use something called a ballistic pendulum. They would hang a heavy wood mass from a rope, and they would fire the bullet into the rope, and when the bullet, into the block, and when the bullet hit the block, everything would swing up. And if you measured how high it swung, you knew how much potential energy you gained. Where'd that potential energy come from? The kinetic energy of the bullet. And if you knew the masses, you could work your way backwards and figure out how fast the bullet was coming in at. It's a very nice little approach. Very elegant. Then they got computerized. No one does it that way anymore, but it still works. Example 2. The diagram below shows 2 pop cans of unequal mass initially at rest. It looks like one of the masses is mass m. The other mass is mass 2m. Now, if you don't like the algebraic, think 5 and 10 kilograms. Oh, it's really stupidly heavy for a pop can, but the math will still work. An explosive charge is detonated. Boom! And between them, and the cans fly apart. You with me, Zach? I know. Okay. What can you tell me about their velocities after the explosion? And using principles of physics, convince me. What can you tell me about their velocities after the explosion? Nico, is there an explode? Oh yeah, show. Go ahead.
Just a guess, but it's velocity for just M.
Say whatever. How about say 20? Okay. 2m would be like maybe exactly 10. So are you saying, first of all, 2m would be slower and half? You are correct. Prove it. Now, you could do it by doing what Sho just did, making up reasonable numbers and crunching them. Can we do this algebraically? Because this one's not too bad, and my little math nerd heart Akemi wants to do this algebraically. So are you ready? Here we go. Akemi, is there an explosion? This looks like a job for momentum. I would start out by saying the sum of the momentum before has to be the sum of all the momentum after. Okay. Before the explosion, what's the momentum? It's meant to be so obvious that it's tough. Before the explosion, what's the momentum? And I'll give you a hint. After the explosion, what must be the momentum then? 0. Now let's see if we can write that algebraically. We would have the momentum of can 1. Let's call this can 1. Let's call this can 2. And the momentum of can 2. Let's see if Sho was right with his little intuitive leap of faith there. Let's see if we can prove this. Momentum, Sho, is what times what? So this is going to be mass 1, velocity 1, vector, and mass 2, velocity 2, vector. So far, so good. I'm going to minus this guy over to that side. Because there's a 0 over there, that's going to give me negative mass 2 V2 equals M1 V1. So how big is mass 2 compared to mass 1? So I'm going to substitute those in. I heard somebody say twice as. I'm going to say this is negative 2m V2, and this is m V1. Yes? Let's tidy this up a little bit. So here's what we're saying. What's the negative telling me about the velocities? Same direction or opposite directions? Opposite directions. And what's that statement there? It's saying V1 flies off twice as fast as V2, which is what you said. You said the smaller can is going to go 20, the heavier can is going to go 10, and 10 times 2 is 20. There's your proof. Sure. Nice. Some terminology. We're going to give explosions names. We have two main types, but we break the second main type into two subtypes. The two main types are inelastic and elastic collisions. Collisions can be inelastic or they can be elastic. In an inelastic collision, the key idea is the masses stick together. A football tackle would be an inelastic collision if you wrap the guy up and hang on to him. A hockey body check would not be. Most car accidents aren't. Most times the wreckage doesn't stick together, although some of them are. Oh, in a completely inelastic collision, momentum is conserved. By the way, is momentum conserved in the next one? Say yes. Is momentum conserved in the next one? Yes. Really what you're saying, momentum's always conserved. Okay. Oh, and you lose kinetic energy. For what it's worth, that's the maximum loss of kinetic energy. If you do like we did back here, if you find all of the kinetic energy before the collision and you find all of the kinetic energy after the collision, you'll find you've lost some. Lots of it has gone into heat. By the way, this is not an inelastic collision. Why is this an inelastic collision? Because the masses stuck together. So a bullet hitting somebody and sticking into the target would be a good example of an inelastic collision. The second type is what we call an elastic collision. They put the word partly elastic in front of it. True. I'll just call it an elastic collision. In an elastic collision, the masses bounce off each other. And the way I remember that is elastic band, rubber bounces. That's how I've kept these straight for, good gosh, 30 years now. Okay, no, I'm not that old. 20 years now. 25 years now. I am that old. Whew. So when I was doing physics in grade 11 and I said inelastic and elastic collisions, I went, okay, I got to keep that straight. Elastic, bounce off each other. Inelastic, stick together. Because unfortunately, Dylan, the words sound an awful lot alike, right? You're just adding a prefix. Okay. Momentum is conserved. You lose some kinetic energy. There is a special kind of elastic collision where the masses bounce off each other. It's called perfectly elastic. If it's perfectly elastic, kinetic energy is conserved. That happens on a molecular quantum level when in chemical reactions, atoms are bouncing into each other. It happens in a make-believe question, say curling, if I tell you that it's perfectly elastic. In my magic physics world where everything works out nice. Okay? There's a couple of more things that a perfectly elastic collision must have. Both objects must have the same mass, and they rebound apart at a 90-degree angle. There is one question on your great big unit review where it says, a perfectly elastic collision occurs, and they don't give you a picture. You can assume they split each other off at a 90-degree angle. You ready? Now we're going to go two-dimensional. You know how I know we're going two-dimensional? Can you see directions in this questions, norths and souths? Oh, and you know it's going to be nasty two-dimensional if you see angles and degrees like example 4. Now I'm going to go very careful and very slow. This seems to have been in the past a unit where kids really, really struggle because they're so used to doing one-dimensional momentum, which is really cross-multiplying and subtracting and pretty good. Here we're going to get tricky with it. You want your calculators out. You want to make sure you're in degrees. Here we go. A 60-kilogram hockey player traveling 2 meters per second towards the north. You know what? They gave me a compass. Graydon, I'm going to go north, east, south, west. Somewhere on my diagram, the number of times I've mixed up east and west would astonish you. So a hockey player traveling 2 meters per second towards the north collides with a 50-kilogram player traveling 1 meter per second towards the west. The two become tangled together, which means it's an inelastic collision because they stuck together. I thought you said hockey body checks were elastic. You bounce off. Yeah, it's not a body check. It's whatever. I'm making up questions. With what velocity do they move off after the collision? What's the very last word of this question before the bracket, right before the question mark? It begins with the letter C. This is a job for momentum. I'm going to still start out by saying momentum is conserved. You'll notice in the 3 types of collisions in the box right above, momentum was always conserved. That's our starting point. Before the collision, what's moving? Player 1, player 2, or both? Both separate or stuck together before the collision? Momentum of player 1, initial, plus momentum of player 2, initial. After the collision, who's moving? Player 1, player 2, or both? Stuck together or separate? Mr. Dewick, we haven't done anything different yet. We're about to. What we're going to do now, and I strongly advise you to do this, we're going to dulp. What direction is player 1 traveling in? Vector. Oh, and not only that, I can even tell you how big this vector is, because momentum is what times what? Got to know that. Momentum is what times what? Mass times velocity. 60 times 2. You know what? This is, I can do that one in my head, 120 long. 120 what? Kilogram meters per second, but 120. Plus, we're going to add 2 vectors. How do we add 2 vectors? We're going to be drawing these tip to tail now. The second player is traveling to the west. Right? What's his momentum? Mass times velocity, 50. Now my scale right now is garbage because that vertical one should be 120. That horizontal one should be 50. I'm going to try and draw these properly now in a triangle. It's going to look like this. Here's my vector triangle. 120 north. 50 west. I think that's better scale, yeah? That 50 is about accurate now. Can you see the resultant? Can you see which direction they move off together? I think westwards and northwards. Left and up. In fact, it's going to be that. This is the final momentum. Wonderfully, Sebastian, I've got a right angle. I can pull out Pythagoras. Most of the time, it won't be a right angle. We're going to be pulling out sine law, cos law, and really going to town. But for here, in this first introductory question, I said, let's make it a nice right angle. So Pythagoras says final momentum squared equals a squared plus b squared equals c squared. Yes? I'm going to get 50 squared plus 120 squared. It's going to be the square root of 16,900. This one stunningly works out evenly because I really fudged the numbers. You get 130. Is the final velocity 130? No. The final momentum is 130. If you know the momentum, how can you find the velocity? Momentum is what times what? Mass times. So if you know the momentum, how can you find the velocity? Sebastian, you're nodding your head. What can I do? Divide by the mass. Okay, so V final is going to be 130 divided by, stuck together or separate? Both masses. 110, yes? $1.18. We're not done. All I've found is the speed. To find the velocity, I need both magnitude and what? At. Oh, I think that's my direction, that angle right there, where the resultant started. Remember? Oh, it was a great review from, holy smokes, way back when, the beginning of this year. First of all, what of what? North of south, east of west, what of what is that going to be? West of north, right? Start out going north, go west of north. to get to that angle. So it's going to be west of north. I need to find angle theta. Let's see. I think I can do that right. Oop, I think I can do that right here. That's going to be opposite, adjacent. Which trig function? Tan? What a few of us will be doing next week? Yeah. How big is the angle inverse tan of that? What do you get? 22.6? I'll go 23 degrees. Is it 22.6 or no? Yeah, so 23 degrees. Okay. Akemi, you may notice a fair bit more showing my work and carefulness and writing than one-dimensional. And this was a right angle. Let's kick it up a notch. Turn the page. Curling with different sized curling rocks. So we're looking down from above like you get in your traditional camera view in a curling rink. Example 4. Yeah. Example 4. Is there a collision? Alejandro, say yes. Do you see angles? This is about as long a question as you'll get all year. Not the longest. There's a couple that have more writing. This is about, though, as much of a mathematically intensive question as you're going to get all year. There's a collision. This is a job for momentum. Before the collision, what's moving? Mass 1, mass 2, or both? Mass 1. After the collision, what's moving? Mass 1, mass 2, or both? Both separate or stuck together? You'll notice I'm leaving lots of space because I know underneath this I'm going to be drawing arrows, pictures. I think the initial momentum is that guy right there. I'm pretty sure that's going to look like this. Yeah? Oh, and I can even tell you how big it is. 16. I went mass times velocity in my head. Is that okay? Bam! They collide. Wait till we start looking at explosions in a couple of lessons. All right. The momentum of this 2 kilogram guy, they gave me a picture. It looks to me like that. Yeah? See it from the picture? Oh, and I can tell you how big it is. It's 2 times 6.7. It's 2 times 6.7. Really? 6.7 times 2. Really? 13.4. Really? He went for his calculator. Okay, making sure. Fine. The second velocity, the second momentum, I don't know what its magnitude is, but I know what it looks like from the picture. Yoink. Yes? And this is going to be momentum of object 2 final, the mystery momentum. How do I add 2 vectors together? Now, where do I have 2 vectors on the right-hand side of my picture, of my little equation? Yes? I'm going to draw those tip to tail. But here's the nice thing. I know what they have to add to. When I add this and this, it better equal exactly a horizontal straight line, because I know that the answer. In other words, when I draw this, it's going to look like this. 13.4. I know to stop there. I know, don't go further. I know don't go shallower because I know apparently when I add those two together, the answer is dead horizontal 16, because that's what the picture told me. I need an angle somewhere in my picture or in the question. They must have given me an angle, and oh yeah, they told me that this angle right here is 10 degrees, which I'm pretty sure is that angle right there. Yes? Oh, here's mystery momentum 2. 90-degree angle? SOHCAHTOA? Do I have a pair? Do I know both of those? No, I don't know the momentum over there. Do I know both of those? No, I don't know the angle down there. Do I know both of those? No, I don't know the angle there. Sine law? It's always, sorry, I can't say always. It's almost always going to be the cosine law. What is the cosine law? Now, it is on your formula sheet, but the cosine law says this. This squared equals this squared plus this squared minus 2 times this cos that. It's Pythagoras in disguise. The cosine law says momentum of object 2 final squared equals 13.4 squared plus 16 squared minus 2, 13.4, 16 cos 10. I think I can go straight to my calculator here. Oh, make sure at the very, very end, I got to get rid of a squared. I have to square root my final thing to get momentum by itself. So it's going to be 13.4 squared. This is where if you got a decent calculator, you're happy. 16 squared minus 2 times 13.4 times 16 cosine of 10. Square root of that. Did I type that in right? 13.4 squared plus 16 squared minus 2 times 13.4 times 16 times cos 10. Do you get 3.64? Okay. They're not moving off together with much momentum. This is not my final answer, so I'll go 3.6434. That's the momentum. It's not what the question asked me to find. What did A want me to find? How can I find a velocity if I know a momentum? Divide by the mass. Which mass? Were they stuck together this time? No, then I'm going to divide by mass 2. Velocity 2 final is going to be 3.6434 divided by, what was mass 2? It must say in the question somewhere. 10 kilograms? Oh, I can do that in my head. No calculator required to divide by 10. 0.364. You never know. Oh, I'm not done, though. You know what I've just found? The speed. What do I need to find? At. Now, put your pencils down and look up for a second. You might be tempted to find this angle right here. The problem with that angle is it's not what of anything. It's not north or south or east or west of anything because it hasn't got, making up that angle, a horizontal or a vertical line. There's no frame of reference. The best angle to find here is going to be this one, because I have to add a little horizontal line. That's going to be north of, I forgot to draw compass rose on here, didn't I? Let's shrink down so we can see the whole picture. That there is going to be north of east. See it? Can you see why I can't use that big curvy one? Because it's not aligned with any part of the compass. That's why I can't use this big angle down here. How can I find that angle? It's the same as that angle, because there's a Z. So this is theta. I can't use SOHCAHTOA. Ah! Wait a minute. Nico, since I just found this thing, I now have a pair. I can now use the sine law. I can now say, I'll do that right here. The sine of the mystery angle theta divided by what's across from it. What's across from mystery angle theta? 13.4 equals the sine of the angle that I know, 10, divided by what's across from it. What's across from it? I didn't know it, but now I know it's 3.6434. You see why I carried a few extra sig figs? Because I knew I'd be using this a few times, actually. 3.6434. I'm going to cross multiply and divide. Or you can say this, sine theta is going to be 13.4. I can move this 13.4 up. Sine 10 all over 3.6434. And the angle is point what? Oh, no, that's not the angle. That's the sine of the angle. Yes? What's my very, 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 very last step? Inverse sine, yeah. 39.7 degrees. 39.7 degrees. Yep. North of east. Is that going to be the hardest question on the test? Not remotely. That's a B. C plus B. This is where it takes a jump. By the way, we're not done the question, because we just did part A. What's part B asking us to find? Okay, we could go conservation, momentum. How much energy before the collision? Only one thing was moving. You would go a half mv squared of the 2 and the 8. After the collision, you would go a half. By the nice thing, energy is a scalar, no angles. You would go a half m v squared plus a half this m, the v that you found squared, and whatever was missing went into heat. We're going to skip B. Turn the page. Chen, could you read example 5 to me, please? Boom!
Whoa.
Yeah? Into 3 pieces. Okay. We're going to temporarily skip example 5. We're going to do a day looking at example 5. Instead, we're going to go to example 6. Okay? Example 6. A 5-kilogram puck, A, moving at 0.8 meters per second to the right, collides obliquely. Obliquely is a fancy word for not head-on. See, if it's head-on, they would just bounce straight backwards in a nice straight line, and it'd be boring. That'd be physics 11. So obliquely, they went at an angle. With an identical stationary puck B, oh, the masses are the same. Puck B then moves at 0.6 meters per second as shown. Find the final velocity, magnitude, and direction of object A. Okay, Let's see. Is there a collision? Yeah? This is a job for conservation of momentum. I'll do my first little line right here. The sum of all the initial momentum equals the sum of all the final momentum. You awake now? You awake? Oh yeah, I know. A, before the collision, what's moving? Mass A, mass B, or both? Bam! They collide. After the collision, what's moving? Mass A, mass B, or both? Separate or stuck together? By the way, you can see I'm doing the same approach as we did yesterday. I'm trying to get you into a routine that way. But what you've got to notice, can you see angles? Can you see angles? You've got to then be saying, hey, I'm going to be drawing pictures, and I'm going to be, if I'm lucky, SOHCAHTOA, probably Sine Law, Cosine Law. My biggest fear is that kids start just dividing and subtracting, not doing vectors, in which case I can give you 2 out of 7. I can't give you any marks for anything else because it's garbage. So after the collision, we have mass A, final, Mr. Dewick, and mass B, final. What's that going to look like? Let's dolp. Mass A, initial, momentum A, looks like that from the picture. Oh, and I can even tell you how big it is because in my head without a calculator, I can go 5 times 0.8. What's 5 times 8? So what's 5 times 0.8? Very good. Wham! They collide. After the collision, I don't know the momentum of object A, but they did tell me it went off in that direction. I got that from the picture. Plus. And they told me object B went this way, and they did tell me the velocity, which means I can figure out the momentum. Second most common mistake, kids put velocities on these arrows. You'll notice velocity is not conserved. What's conserved? Momentum. Here, it's going to be 5 times 0.6. I'm pretty sure, Cole, that's 3. How do I add those 2 vectors together? Draw them. Tip to tail. And here's the nice thing, Sam. I know that when I add these 2 here, tip to tail, the answer is going to be a horizontal line, which means I can figure out how to draw this triangle. It's going to look like this. I got to go down here. Mystery momentum of A final, which I don't know. Yoink. 3. And they add together to form exactly a lovely horizontal line 4 long. I need an angle. So the angle that they gave me was this one, which I think is this one. Well, that doesn't help me. Oh, wait a minute. It's also that one. Because a little Z there. So this here is 29 degrees. You okay with that, Kevin, or did I lose you? Is that okay? Okay. SOHCAHTOA? No. Pair? No. You know what? It's cosine law. The other way you can tell it's cosine law is whenever you have side, angle, side. So 2 sides and the angle between them, and you're trying to find the one across. That's cosine law. So what's the cosine law going to be? Momentum of A final squared equals 3 squared plus 4 squared minus 2, 3, 4 cos 29. This isn't the longest question of the year. It's close. This is the most having to concentrate and bring various skills. There's 2 questions when we do orbits that are longer, but it's just a huge mother of an equation, type like crazy on your calculator longer. Not, wow, now what? Wow, now what? Wow, now what? Grady's laughing. I'm happy he's happy. No, I'm not. Oh, sorry. Oh, square root, square root, square root. The mystery momentum is pretty much bang on 2. I'll go 2.0023. I'll carry a few extra sig figs because I know I'm going to be using this. How can I find the velocity? Because this is the momentum. Divide by the mass. What was the mass? 5? .40 meters per second. That's the speed. Now I make it a velocity at. Look at my picture. Here's the momentum of object A final. So I think its direction is that there. I think this is the angle theta that I want to find. I think it's going to be north of east, I think. Oh, I need to find a magnitude of the angle. This is a job for the sine law. I've done a lousy job of allocating. Oh, no, I can fit it in right here, I think, if I'm careful. Sine of the mystery angle theta divided by what's across from it equals sine of the angle that I know divided by what's across from it, which was 2.0023. I think I'm going to get sine theta equals 3 sine 29 all over 2.0023, and then I'll inverse sine that puppy. You get 46.6 degrees? Yeah? And what did we say that was? North of east. Turn the page. North of east. Okay. All we're going to be doing is repeating this theme. If we're lucky, it's SOHCAHTOA. If we're unlucky, it's sine law, cosine law. I can do a couple of more if you guys want me to, or if you think you kind of got the hang of it and you just want to try it, because you really, this is where you really need to practice a few of these. I don't mind stopping the lesson here and just giving you the homework. What do you guys want? A couple more or the homework? Okay, I heard homework was kind of the dominant one there, so we're going to press pause for a second, and I got to hand out the homework. Okay, first of all, homework number 1 is, this is momentum take-home quiz number 1. This is all linear, straight line, no angles. First quiz. Okay? I'd never give you a quiz on something I just taught you. Oh, does that mean you can expect a take-home quiz with angles and stuff in the future? Sure, but not this one. Try that, and then homework. So I had to give it to you on a separate page. Number 1 you can do. This is still straight line linear. What, the IJK thingy?
Yeah.
in physics 12, in first year university physics, when you go 3 dimensions, it's too awkward to be talking about north-south because this is not north, despite the fact that on our paper we often make up north. So we say left-right is I direction, up-down is J direction, K direction is into the page or out of the page. And you talk about something being 3I plus 2K plus, that tells you where it's located in 3 space, in 3-dimensional space, since you asked. We can do number 5. So far I've said number 1 and number 5. Number 6. Boy, this doesn't have as many as I wanted. You know what? I think your other homework is going to be, and you don't have the answers for this, but your other homework is going to be try example 7 and example 8 from the lesson, and I'll give you the answers to it next class. Okay? From the actual lesson. 1, 5, 6, 7. 1 for whatever I assigned from the homework and then from the lesson. Yep.